So I'm going to be talking about WebAssembly and the death or future of JavaScript. And there's a bit of a funny joke behind this, because the first time I did this presentation was about 6 months ago. I've been interested in WebAssembly for quite a while, and I gave a talk at a meetup, and a lot of people at the time were talking about whether WebAssembly was going to be the death of JavaScript. So I thought, I'll do a talk that asks that question. So it was WebAssembly and the death of JavaScript, ? They put that video on YouTube, and whoever put it on YouTube left out the question mark. So what happened was, people read it as WebAssembly and the death of JavaScript, and it got a lot of views. And don't read the comments; they're a little bit rude. So I changed it to the future of JavaScript. Yeah, I'm not going to make that mistake again. So yeah, a little bit about Scott Logic and myself, and I guess why I'm here. I work for a company called Scott Logic. We're based in the UK, and we write applications for the financial domain and for things like energy trading and so on. This is the sort of thing we build on the web, some quite complicated looking platforms. We write, for example, we've got clients in Scandinavia like Saxo Bank, where we do a lot of work on their web-based front ends. So basically we write a lot of JavaScript. And as mentioned before, the reason I'm actually here is we're quite heavily involved in a conference series called FinJS, which predominantly has been in London and New York. Today, for the first time, we're going to be in Stockholm. So that's the reason I'm over here. And actually, if you look at the bottom, this guy, Chris Price, is one of my colleagues, and he's going to be presenting today, and he's doing a cool talk about TensorFlow.js, so machine learning and neural networks in the browser. Another thing like WebAssembly that we're interested in but don't really use, but in the future, hopefully. So yeah, back to my talk. I'm going to start off with a brief history of the web, because I've heard that's how you're supposed to start every talk about the web. I'm not going to talk about all of the web, because that would take a little while. I'm going to talk about the languages of the web and how we write interactivity within the web. And I guess it all started about 22 years ago with this language called JavaScript, which, hands up if you use JavaScript. Yay, I'm in the right room. Thank goodness for that. So JavaScript, as you're probably aware, was invented by a chap called Brendan Eich, and he invented it in around about 10 days, which I guess for people when they're learning JavaScript, they generally go, whoa, what is that? And part of the reason is it was very much developed in haste, and it's quite surprising it's stood up this long. Brendan said it was a rush job that was barely good enough to survive, and I was actually at the conference earlier this year where he said that in person, so I'm happy to quote him on that. He's well aware of the limitations of the language that he created. So as you can imagine, that was 20 years ago, and many other languages have tried to gain a foothold in the web. We've had Java applets, ActiveX from Microsoft, Flash from Adobe, Silverlight again from Microsoft, Dart. And it doesn't matter, they're all dead and gone. 2018, we're still just using JavaScript, which is pretty amazing. But the interesting thing from my perspective is the way that we're using it has changed considerably from when it was first conceived. When Brendan invented JavaScript, it was intended to be a language for adding a small amount of interactivity to what were otherwise static websites. So think things like form validation. We're not really doing just that with JavaScript these days. We're doing so much more. And the first observation I'd like to make is that we are collectively writing a lot of JavaScript. And just to prove that, the other day I started up a React app. And if you use React, you'll know that pretty much the standard approach to that is to use a thing called Create React App. It's a nice, convenient way to scaffold a React app. So I installed that and had a quick look, and I'd just downloaded 79,000 lines of JavaScript from NPM. So yeah, I think that really does underline the fact that we are collectively writing a lot of JavaScript. We're writing it for all sorts of reasons. We're not just writing it to run within the browser. JavaScript is our tool chain. JavaScript runs on the server. JavaScript runs on mobile devices. So we're writing a lot of JavaScript in a lot of different places. But one of the more significant things is the JavaScript we write these days very rarely makes it to the browser untouched. It often goes through a complex series of transformations that, to be honest, a lot of the time I don't understand what's going on under the hood anymore. I know that I write in perhaps TypeScript, or I use Angular 2, for example, which has got all kinds of fancy decorators, and somehow that gets mangled into this mess that actually ends up within the browser. And a few years ago, this caused a guy called Scott Hanselman to make the observation that JavaScript is the assembly language of the web. He wrote an interesting blog post about that 8 years ago, and that was a flame war right there. Loads of people were saying, that's absolutely ridiculous. If he wrote that post now, everyone would go, yeah, fair point. That's the way we do it these days. But there's a bit of a problem. JavaScript actually isn't a very good assembly language. So the whole fundamental way that we're writing JavaScript and deploying it to the web is fundamentally flawed. And I'd just like to show you why. So this is what happens within your browser as it loads JavaScript and tries to execute it. This is a bit of a simplified schematic that I took from a Mozilla blog post that looked at, I think it's SpiderMonkey or Odin Monkey or some kind of monkey, their JavaScript runtime. So this is a simplified view of what happens. So over on the left-hand side, the characters come over HTTP, and the first thing it has to do is it has to parse that into an abstract syntax tree. From there, it generates the underlying bytecode, which can immediately be run in an interpreter. Then that's the way that JavaScript worked maybe 10, 15 years ago. It was all interpreted. It was a little bit slow. These days, the stuff on the right-hand side is getting very sophisticated and more sophisticated every year. So what happens is it has a look at the JavaScript as it's running, and it starts to make assumptions about how the code will execute at runtime. So for example, if you've got a function where you pass in a couple of parameters, it will observe that and look at it and say, oh, most of the time those are integers. I can optimize for that. I can compile down to the underlying machine code or assembly language to make that run faster. So it will do just-in-time compilation to make your code run faster, and then there'll be further optimizations it can make and further optimizations. Unfortunately, those optimizations are made based on assumptions, and sometimes those assumptions are false. And what happens in those instances is it has to push it back down to one of the lower tiers of optimization. And some of the browsers, I think Safari has 4 different levels of optimization that are going on under the hood. So if you think about it, your JavaScript code is taking a very long and convoluted route to this point at the very far right, which is where you want it to be. And this has a significant impact for end users. Recently, there's been a lot of talk about things like time to first meaningful paint, time to interactive. It doesn't matter what kind of application you're developing, you're deeply concerned about how long it takes to be visible and usable by the end user, especially on mobile platforms. And as you can imagine, this is a pretty convoluted way of actually getting your JavaScript code into the browser to do something. It's definitely not by design. And as you can imagine, this is a very simplified schematic of the timeline of what happens. So if you look, it first is parsed, then it's compiled and optimized, then re-optimized, then it's executed, and then at the very end, the other thing that happens is we have garbage collection as well. So this is a very long timeline before something interesting happens. And this is an interesting quote from the paper the team behind WebAssembly published. They said, "The web has become the most ubiquitous platform ever, and yet by historical accident, the only natively supported programming language for that platform is JavaScript. This has happened by accident." And you might think that was written by a bunch of JavaScript haters. It's not the case. These are written by the people that work on the browsers. They love JavaScript, but they're honest enough to recognize its limitations. So WebAssembly, in a single sentence, WebAssembly or WASM is a new portable size and load time efficient format suitable for compilation to the web. So before delving into any of the details, I think the interesting thing here is to acknowledge that it's addressing some of the core weaknesses that JavaScript has, and unfortunately JavaScript cannot escape at the moment. So it's size and load time efficient. They've designed it for compilation to the web. We all compile our JavaScript, so they've decided, let's design a platform that's intended for compilation, not JavaScript, which is just a bit of a strange fit. Now, before I go into WebAssembly in a bit more detail, I think it's useful to have a look at ASM.js, which is one of the key parts of the history of WebAssembly itself. So just a show of hands, have you heard of ASM.js, or do you know what it is? Okay, show of hands if you've heard of it, and keep it up if you know what it is. Okay, a few hands dropping. I must admit, when this came out, it was probably 4 or 5 years ago, I looked at it, thought, wow, that's crazy, I don't understand, and then walked away. And I think a lot of people have done that. It's only when WebAssembly appeared that all of a sudden it made a lot of sense. So I'll briefly introduce you to ASM.js. So at the top, you've got a simple function written in C. The reason for that is ASM.js is built on top of the LLVM compiler, and it requires a statically typed language. So running it through the mscripten compiler, and that's the command line required to do that, the bit at the bottom is what it spits out. So the first thing to realize here is it's spitting out JavaScript. This will run in any browser, but it's not like any JavaScript we currently know. So if we look at the top here, we've got A equals plus A, so it's coercing A to be, well, it's the kind of numbered coercion that you do. B equals B or 0. What these are type hints. This is basically telling the runtime that A is a float and B is an integer, as you can see from the signature at the top. And you can see at the bottom the same type hint for the return value. The for loop has been unfolded into a do-while loop, and all kinds of other weird things are going on. And that's when I first saw ASM.js, I thought that's weird and didn't understand it. Going back to how the browser actually works, this is what it's attempting to do, and this is actually what it achieved very nicely. So, with ASM.js, the characters are parsed into an abstract syntax tree, just like any other language. But the key is this bit of text at the top, use ASM. What that does is that allows the runtime to immediately take that abstract syntax tree, which is a very restricted subset of the JavaScript language, and immediately push it all the way over to the right to a highly optimized and highly performant compiled version of the code because of all the type hints and the restricted language that it's using. So with ASM.js, whilst it looks like JavaScript, at runtime it can perform so much better than JavaScript. And as a little demonstration, the team behind it they took the Unreal game engine, which is written in C++, converted it to ASM.js and showed it running in the browser, which was super exciting. It's pretty cool. So the reason they did that was they wanted to demonstrate that there was a fundamentally different way that you can approach the web as a runtime. Previously, people had concentrated on things like the plugin model, the idea of, okay, we've got JavaScript over here, it doesn't quite do what we want it to do, so we'll ignore it and we'll plug something else in. And unfortunately, everything they tried to plug in was proprietary. So Flash was Adobe, Silverlight was Microsoft, and because of the proprietary nature and because of the competition between browser vendors, that was just never going to work. You were never going to get Google say, oh yeah, Silverlight looks great, we'll go with that. It's just not going to happen. With WebAssembly, what they did was and ASM.js was they showed that you can actually create something that lives alongside JavaScript and complements JavaScript rather than replacing it. Another interesting thing about ASM.js is I showed you the type hints. The memory model of ASM.js is quite surprising. All it is an array buffer, and it reads and writes to the array buffer. That's its memory. So WebAssembly, the working group was formed in 2015, and the MVP was released just 2 years later, which is pretty amazing. And if you study ASM.js and WebAssembly, there's so many similarities. ASM.js was effectively a kind of blueprint for WebAssembly. But if you've worked in the web for a while and looked at how long it takes for technologies to mature, things like web components, it's been going 10 years and it's still not there yet. Things like even simple stuff like CSS grid. I mean, how long can that take? I first heard about that 10 years ago and it's not done yet. And here they've created a new runtime in 2 years, which is pretty impressive. And as I mentioned, it's here now. That 72% is probably more like 75%. It's in pretty much every major browser, and by major browser I mean not IE. It's in all the good ones. Yeah, and it's pretty much good to go at the moment. So I want to show you a little bit more. So ASM.js introduced the concept, so I want to show you a little bit more about what WebAssembly itself actually is. So if we go back to exactly the same example, a power function written in C, and if you want to give it a go yourself, I'd recommend visiting WebAssembly Studio. So Unfortunately, WebAssembly typically requires things like the Rust compiler or the C compilers. If you don't have that on your machine, it's a lot of stuff to install, or you could just use Docker. But an easier way to do it is to just use WebAssembly Studio on the web if you just want to dabble. And when you compile that code to target WebAssembly rather than ASM.js, this is what comes out. You get a binary or a WASM file. It's much easier to actually understand WebAssembly in its text format, which has got the extension WAT or WAT. And some of you might have seen the talk WAT, which I think it's a sly nudge reference to that talk. But basically, if you've done any assembly language, you'll immediately look at this and recognize that it does have the feel of a kind of assembly language, although it's not like any other assembly language I've seen. It's got quite a few constructs that you typically wouldn't see in assembly language, things like ifs and functions and so on. But it's generally it has a very low-level feel to it. Now, what do you do with that WASM file? You've got a binary file, and you've somehow got to load it in the browser. Currently, what you've got to do is quite literally use the fetch API, or in this case, I was loading it using Node, so you read it as a file. And then what you do is you create a WebAssembly module, you instantiate it, and then immediately you're able to interact with the functions that it exposes. And if you try to inspect that power function, it will look just like things like math.sign. It will show up as effectively a native function. So at the moment, to run WebAssembly, it needs to live within a host, and currently that host is JavaScript, which is limiting, but we'll get onto that in a bit. It gets a little bit more tricky though. WebAssembly has a very simple type system. It has 4 types, and they're all numbers. Two integer types, 2 floating point types. So how on earth do you do this, where you have a string and you're returning a reference to it, a hello WASM example? That's actually a little bit more tricky. So here, to get that to work, what we're doing is the first 4 lines here are pretty much the same. We're reading the WASM file, we're creating a module. Next, what we're doing is we're obtaining a reference to linear memory. So what happens is WebAssembly requires effectively an array, which is the working memory of your WebAssembly module. That array is exposed to JavaScript as well. So with JavaScript, you can peek into the memory that WebAssembly is operating on. So that's how you start passing richer types backwards and forwards. So in the previous slide, this is a character pointer. When it's compiled to WebAssembly, that pointer just becomes an integer. It's an index to a location within an array. And here we're just using a text decoder to decode it. It's a little bit complicated just to say hello world. So a little bit more about the architecture. So WebAssembly itself is a stack machine. As I mentioned, it's got 4 types. An interesting one is it's 64-bit. So that's an immediate advantage. Years and years ago, I worked for a company called Lehman Brothers. You might have heard of Lehman Brothers? Yeah, good. Interesting company. I was working on a thing called the securities lending platform. Now, Lehman Brothers had a lot of money, and they made a lot of money by lending a lot of money to other people. And quite a few of the contracts that we were managing were really, really big. And because of that, you couldn't fit that number into a float because of the size of it. It was we needed more than 15-digit precision to represent the sums of money that were passing around. Good old Lehman Brothers. So the need for 64-bit and higher precision it's not just required in the financial world, it's required all over the place, and WebAssembly has that baked in. Another useful thing it has is support for streaming compilation. So as I showed you previously with JavaScript, in order to execute it, you need to load and construct the AST for all of the JavaScript because of the way things like hoisting works and so on. WebAssembly is designed in such a way that it can actually start compiling it before it's loaded the whole module. It's also got very simple validation rules, the rules that are required to check the integrity of the application. Again, a lot of this is built around speed. As I mentioned, linear memory shared with JavaScript, and it can export and import functions. So as well as exporting a function to JavaScript, a JavaScript function can be imported, so you've got this two-way interface. So what does that all mean? Well, it's actually quite good. So at the top, this shows you the timeline of loading and executing JavaScript. This isn't a real one, I haven't performance measured it, but conceptually this is what it looks like for WebAssembly. We decode, compile and optimize and execute. There's none of this optimization and re-optimization and tiers of execution. There's no garbage collection. And obviously there's no parse as well. It's just a decode step. In practice, it happens so much faster than JavaScript. Now, in the future, WebAssembly is going to gain all kinds of different features. At the moment, WebAssembly itself is an MVP. That's how they managed to ship it in just 2 years. In future, it will gain things like garbage collection. Threads is something they're working on. By threads, I mean it's going to have language support for things like atomics and shared array buffers. So it won't have threads itself, but it will have the constructs that allow it to work within a threaded environment. Host bindings is going to be a big one. As I showed you, just simple things like returning strings is actually quite challenging. There's a proposal in progress at the moment for host bindings, which will be a sort of declarative way of code generating those bindings and making it very easy. SIMD, single instruction, multi-something or other, it's performance stuff. Exception handling as well, they're adding that to the language, and lots more. So this is the very first version of WebAssembly, and it's going to evolve quite rapidly.
Can I ask a question?
Yeah, go for it.
I'm thinking like on the DOM interaction in JavaScript today. What's the plan for that? I mean, if you want to replace, or if you would like to use WebAssembly instead of JavaScript, you would like to be able to integrate with DOM. What's happening there?
There are two specifications that will help with that. One is the reference type specification. What that does is that allows WebAssembly to hold references to objects on the JavaScript heap. So at the moment you just can't do that. The only thing you can do is hand off data one way or the other by copying effectively. So reference types is very important. So it means that your WebAssembly application can hold reference to JavaScript objects and DOM nodes. Then through host bindings, that will allow a much richer integration between the two. What they've done is the APIs. The DOM APIs use, I think it's WebIDL, that's their interface description language. The team behind Rust have written a tool that converts WebIDL into... They've basically taken the host binding specification and gone ahead and implemented what is effectively a polyfill for it. Then used WebIDL to generate all the web APIs, and they've published a crate called the WebSys crate. So if you're working within Rust at the moment, you can use all of the current DOM and HTML APIs effectively through a polyfill. So it is coming. At the moment, you can do all of this, but you have to write a lot of the glue yourself. Basically, in the future, the glue is going to be something that's taken care of by your tool chain, and there'll be less glue required because of the newer features of WebAssembly. So yeah, it's getting better. At the moment, it's a little clumsy. So what are people doing with WebAssembly at the moment? So C and C++ had a bit of a head start because they were used by ASM.js. It's based on the LLVM toolchain. At the moment, it's got support for things like OpenGL as well, through OpenAL. So people have been using this already in production for things like PS-PDF kits. So there's a company that has PDF rendering as a product, and at the moment, all their PDF rendering is done on the server. They were able to take their PDF rendering library, compile it through Emscripten and WebAssembly, and run it within the browser. And from what I understand, the PDF rendering is actually quite challenging. It's hundreds of thousands of lines of quite dated C or C++ code. So for them, that was a big success. And the team behind this have actually have a website which is a WebAssembly benchmark, because this is one of the first quite large real-world use cases. They're publishing it as a benchmark, and the browser manufacturers are actually tuning their browser to make these examples work faster. Another one at Google I/O, company AutoCAD that does design tools. Their software is probably 30 or 40 years old, and like many companies, they've tried all kinds of different approaches to bringing AutoCAD to the web. They've done a Flash version in the past. They started hand cranking their own JavaScript and HTML version, and in each case they realized that the investment required to create a fully featured version of AutoCAD on the web was going to be huge, because they've already invested 10 years duration but hundreds of years of developer effort into creating this. But through WebAssembly, they were actually able to take the fully featured version of AutoCAD and compile it and run it in the browser, which was pretty amazing. At the moment, it's a pretty hefty beast. It's about 30 megabytes or something like that, so they're planning on stripping some of the stuff back. But for them, it's an avenue that wasn't possible before. The only way they could do it previously was some form of rewrite. This is one that at Scott Logic we've done. We worked with a company called Active Financial, and they provide streaming financial data for high-frequency trading. So their product is two things. It's high-frequency pricing information and a library which decodes their custom protocol, which then allows people to do things like high-frequency trading. We took their library code, compiled it to WebAssembly, changed their protocol to work over WebSockets, and we're able to run the whole thing in a browser. And again, it's great. We were able to take a legacy code, well, not a legacy code base, a code base where previously the only route forward would have been to start looking at the C code and rewrite it in JavaScript. Here we were able to bring it straight to the web. And then people are doing fun things, like you can get Vim running in a browser. And you know what people love about this? It's got a little close button up there, you can close it. Java and C#. These languages are a little bit more challenging to bring to WebAssembly because they require a garbage collector. And WebAssembly, again, to keep it simple to start with, doesn't have a garbage collector. So what that means is projects like Blazor, which is a Microsoft project, what they're doing is they're using Mono and compiling that to WebAssembly and running that within the browser. And that brings its own garbage collector with it. At the moment, they're experimenting with a couple of different modes of operation. One of them is interpreted mode. So with Blazor running in the browser, you can actually send DLLs to the browser and it will run on the Mono platform within the browser, which is pretty insane. The other thing they're looking at is ahead-of-time compilation. So rather than taking DLLs and sending them to run on an interpreter, do ahead-of-time compilation from the DLL straight to the WebAssembly instruction set, which in the long term is probably a better way of doing it. Now, Blazor itself is an SPA, a single-page application framework. So as well as the underlying .NET runtime, they're using Razor templates. I think that's an ASP.NET technology to allow you to actually do all the DOM interaction. JavaScript. You might think, why on earth would you want to compile JavaScript to WebAssembly? I think a lot of people will want to, because all the benefits of WebAssembly, the significant reduction in time to deliver interactivity to the web, why wouldn't we want this in JavaScript as well? JavaScript is a bit more challenging though. Firstly, it needs a garbage collector. Secondly, it isn't statically typed. And currently, all of the languages that compile to WebAssembly are statically typed languages, just because it's obviously a lot easier. There are a few experiments that I've seen at the moment. One of them is called Walt, which is a JavaScript-like syntax for WebAssembly. So it basically takes that the WAT, the WAT text format, and does a sort of thin layer of JavaScript on top of it. I think that's a fun and interesting experiment if you want to just write a small amount of WebAssembly. I don't think it's going to be terribly useful for any significant application. I think the more interesting project is the one called AssemblyScript, and that's a TypeScript to WebAssembly compiler, because TypeScript allows you to write statically typed JavaScript. So that gives JavaScript developers a route into WebAssembly. Although again, it's waiting the garbage collector within WebAssembly to become super powerful. So I actually had a go with AssemblyScript a little while back. Has anyone used D3 before? Yeah, it's a fun sort of library. One of the things I quite like, one of the many fun things in D3 is a thing called force layout. So this basically is it gives you things like n-body physics and Hooke's law for springs and so on. So this is a simple force layout. Currently, obviously, all the physics is done within JavaScript. So what I did was looked at the D3 code, which is fun because Mike Bostock, the guy that wrote it, writes weird JavaScript. He has an odd style of JavaScript. But tried to work out how it worked. After a few hours of reformatting it, I could understand how it worked. But anyway, I took that and turned it into AssemblyScript. So I effectively did the JavaScript to TypeScript sort of recompilation, effectively. I added all the type information that was required, and then through AssemblyScript, I was able to compile that to TypeScript. So what you're seeing there is force layout, where all the actual calculations for the layout are being done by WebAssembly. And the great thing is, because I was doing that under the hood, the API that presents is exactly the same as D3. So I was able to rip out the JavaScript code, replace it with WebAssembly through AssemblyScript, which is TypeScript, and then make it look exactly the same, which is pretty cool. Rust. You'll probably see a lot of people talking about WebAssembly side by side with Rust. And there are a few reasons. One is that Rust doesn't require a garbage collector. The other is that Rust at the moment is one of the most popular and one of the most... it's rising in popularity like nothing else. It's quite an elegant language. But at the moment, it's a bit of a niche language. And the reason I say that is because, to my mind, anything that isn't on the web is a niche. So everything other than JavaScript is a niche. Maybe I shouldn't say that. But it is. They originally used mscript to compile Rust to WebAssembly, but they've now got a much better and simpler toolchain. And I saw this quote in someone's blog post: "We're poised to be the language of choice for WebAssembly." And the reason they think that is, firstly, it's a really nice looking language. I only looked at it about 6 months ago because I was interested in writing WebAssembly, and I didn't really want to go back to C or C++. So I thought, oh, that looks nice, I'll give that a go. And they've got a great window of opportunity, because right now, you've got C has first-class support, C++, and Rust. All the other languages that are popular, whether it's Java or C#, they've got to wait for garbage collection to come along. So Rust at the moment has an opportunity to really push forwards and become, a really fantastic first-class language for the web. And the Rust team are very much behind this. They've been creating all kinds of tooling, polyfills, and all kinds of things that actually make it a lot easier to write Rust for the web. So this is one of the first things I had to go with. For years and years, I've always wanted to write an emulator of some sort. And when I was a kid, I had an Amiga. Has anyone here have the Amiga or know the Amiga? Yeah, it was a great computer. So I thought, I'm going to write an Amiga emulator. And then I found out, actually, that's really hard. The Amigas had a highly customized chipset, and I thought, that's going to take me years. So then I thought, I'll write a Game Boy emulator. That's a bit easier. And I found that was quite hard. So then I found this thing. It's called Chip 8. Has anyone heard of Chip 8? Okay. It's a bit of a funny one. I read back from the guy that invented Chip 8. There's, on the Wayback Machine, you can find the magazine where he actually published the specification for Chip 8. It never had its own dedicated hardware. It was, at the time, it was already a virtual machine that would run on a number of machines in the 1980s. It was 4K, where the first 512 bytes was the emulator. So because it was designed to be very, very simple and very, very small, it's actually really easy to replicate these days. So it's kind of my first emulator project. So I wrote this emulator using Rust as a way to firstly try out a bit of WebAssembly, and also to kind of scratch that itch of, I've always wanted to write an emulator. So there it is. On a more other people are doing more useful things than me with it. And a team at Mozilla did something quite useful. One thing you'll probably notice is I haven't said much about performance yet. And there's a very good reason for that. There's a lot of misinformation about WebAssembly and performance. You'll see it. I've seen no end of blog posts saying that WebAssembly is 100 times faster than JavaScript. They're all wrong. That's gibberish. If you've done anything with JavaScript and performance and comparing it to native languages or statically typed languages, JavaScript is incredibly fast these days. If you take anything like a Mandelbrot generator or a factorial function, the difference between WebAssembly and C is negligible. We're talking 20, 30%. So how can you say WebAssembly is better for performance? There's not that much of a window to improve. But there are other metrics than just raw performance. In order to achieve that performance, obviously you have to go through all those tiered profiling and compilation stages, so it takes a little while for JavaScript to warm up. I think when you're looking at performance, you need to look at real-world use cases, not micro-benchmarks. And this is one of the first real-world use cases I saw. So, source maps. You've probably come across them. As I mentioned, JavaScript goes through multiple transformations, and to be able to breakpoint and go back to your TypeScript or your React code, source maps provide the mapping between the garbage that ends up in the browser and what you've written. Source maps, obviously, written in JavaScript, of course. And source maps, for large projects become quite slow because, again, it's using JavaScript. So what this team did was they rewrote the source maps algorithms effectively in Rust and compiled it to WebAssembly, and then compared the time it takes from hitting a breakpoint to actually being able to see your code. So a real-world performance benchmark, not a micro benchmark. And what you can see here is they tried it across multiple browsers, and in Chrome, it's maybe getting close to maybe 40% improvement. In Firefox, it was considerable, more than half the time taken to hit the breakpoint, and the same with Safari. But another interesting thing here is you see the spread. This is because the runtime performance of JavaScript is unpredictable because of the way that it works. There's very little spread in WebAssembly. It's got a much more predictable runtime performance than JavaScript. So this is interesting. In real-world benchmarks, it does have a significant improvement because of all the baggage that JavaScript brings with it. Other languages, Go, preliminary support landed a few months ago, and basically, name a language, someone somewhere is trying to compile it to WebAssembly. Perl, Python, Swift, Kotlin, the Kotlin team are doing quite a lot of work on it. Yeah, pretty much everything will compile to WebAssembly soon. But something I find even more interesting is that WebAssembly is actually a bit of a misnomer because it's not assembly. You've seen that. It's an assembly-like instruction set, but it's not an assembly language for a specific chip. But also, more importantly, it's not just for the web. The whole WebAssembly specification has been written in such a way that it doesn't mention JavaScript. It doesn't mention the web explicitly. It refers to the runtime that sits around it as the host. And that host can be anything you like. And as a result, people have been taking and building JavaScript WebAssembly virtual machines. You can find WebAssembly virtual machines written in Rust, for example, which are standalone virtual machines which you can then wrap a host around. A really interesting use case for this is blockchain. I won't try to explain what blockchain is because I don't understand it either. But one of the challenges that the Ethereum team have is that they created their own language for smart contracts called Solidity. And the problem is when you create your own language, it's a barrier to entry. So the Solidity contract language, I think, is a decent language, but very few people know it, and very few people have learnt it. And if you've heard about, I think it was the DTO hack. I don't know if anyone's aware of that. There was a particular smart contract that was created called DTO. It was a way of crowdfunding. So you could be part of this network that had smart contracts which governed how you crowdfunded. So it was a bit like Kickstarter, but on the Ethereum network. There was a tiny flaw in the Solidity contract behind DTO, and a hacker managed to drain away about $70 million worth of Bitcoin through this one fault in the Solidity contract, and it was untraceable because of the anonymity around blockchain. So, yeah, that's part of the struggle they have, is that they've got their own language and very few people understand it, and those that do probably don't understand it enough. So the Ethereum team are interested in using WebAssembly as a runtime for executing smart contracts. And what that means is that people can start writing smart contracts in Rust, in Go, and hey, JavaScript one day. You know, so it's quite interesting. Other people are using things like WebAssembly to create runtimes that remove some of the protection rings. At the moment, when you execute an application, there are various protection rings before it can hit kernel and I/O code. With WebAssembly, WebAssembly is inherently safe and sandboxed, which means you can remove some of the operating system protection layers. So people are doing crazy stuff with it. So finally, I'm going to finish with some crystal ball gazing of where I think all of this might end up one day. This year, not that we've got much left of it, I think Rust, C, C++ are going to be used for production, performance-critical and algorithmic tasks. I'm already seeing this at the moment. So things like source maps, the changes that they've made there, they're releasing them under NPM. So if you're using a version of Node that supports WebAssembly, which you no doubt are, very soon that could be using WebAssembly just to speed that up. You're seeing things like cryptographic algorithms being released onto NPM, again using WebAssembly. And Rust as well. Webpack and improved tooling. Of course, the there's a lot of work involved in integrating WebAssembly into the JavaScript ecosystem, things like NPM, things like the module system. And there's a lot of work going on in Webpack at the moment to work out how to make WebAssembly a first-class citizen. The other languages, Java, C#, TypeScript, I think we're going to see a lot of creative experiments, but I don't think any of that stuff is really going to be production ready quite yet. Native node modules, another irritating thing. Anything like, I think Phantom.js, or is it Chrome driver? There are quite a few tools that we use on a day-to-day basis which are native node modules, and that causes friction. With WebAssembly, you can potentially take those, compile them to WebAssembly and make them a first-class citizen, once again, so it doesn't have to recompile when you install. Also, WebAssembly itself is going to improve. We haven't seen a version 1.1, or we haven't seen a next release yet, but I don't think it will be long. Quite a few of the browsers have various future features available through flags at the moment. So reference type support is available in Chrome at the moment. I think, what was it, Threads as well appeared just 2 days ago in Chrome as well. So it won't be long before we see WebAssembly improve in it of itself. Next year, I'm sure some of these will actually become mainstream and will be released, garbage collection, host binding, and so on. And what that will mean is it will become easier for languages to start targeting WebAssembly. I think as a result, Java and C# will become production ready. To be honest, maybe not Java. I'm not seeing quite so much activity within that community, but Microsoft are all over it with Blazor. I also think we'll see another wave of mobile, desktop, and server-side UI frameworks retargeting the web. Do you remember that old mantra, write once, run everywhere? Which basically means take your application and make it horrible everywhere. It will come back, and I've seen a number of the old write once, run everywhere vendors moving to WebAssembly. It's not my kind of thing. I don't think that's the best way to work. Mobile and desktop are so different that there's not a lot of value in that, but it won't stop people trying. I also think for a lot of people, performance gains will fail to materialize and we'll get a backlash from early adopters. WebAssembly is a little bit complicated, and understanding whether your use case is actually the right use case for WebAssembly is a little tricky at the moment, and I think a lot of people will end up adopting it and realize that they shouldn't have adopted it, and what do? They'll blame the technology. It's what we all do. And also, heavyweight productivity tools will start moving to the web. And I first did this talk, as I said in the meetup about 6 months ago, and said Photoshop and AutoCAD will come to the web. Google I/O, someone from AutoCAD was standing up. I think we'll actually see AutoCAD have this as one of their commercial options. It wouldn't surprise me if things like Photoshop, things like video processing, all the kinds of things that you just couldn't do on the web will become possible. Beyond, I honestly think JavaScript will compile directly to WebAssembly at some point in the future. TypeScript, I don't know if you use TypeScript much. Do you use it? One of the things I find most elegant about the way that the team behind TypeScript approached it was they tried very hard to align their language to the future of JavaScript. So they introduced things like classes before classes were, I forget which version, ES6, 2016 or whatever it is, but they introduced numerous features which they knew were part of the TC39 process ahead of time. There are specifications, there are proposals at the moment for baking in some of the TypeScript concepts into the JavaScript language itself. So things like types will likely become a first-class yet optional part of JavaScript in the future. So as some of the TypeScript concepts leak into JavaScript, JavaScript will become a language which will more easily compile to WebAssembly. So it wouldn't surprise me in the future if we can start typing maybe use WASM at the top of a file and it will compile to WebAssembly. Another more radical thing is I think native Android apps will die out. Google are quite keen on progressive web apps. It makes use of the ubiquitous technologies of the web. WebAssembly will allow them to open up that option to applications that are more gaming oriented, more processor intensive, so the ones where JavaScript itself is the fundamental weakness. Everything else about progressive web apps works really fine, but sometimes the runtime lets us down. Not going to say anything about Apple and iOS, who knows. Windows Store, I think, will move to progressive web apps and WebAssembly. Windows Store as a concept, to my mind, didn't really work. Windows themselves Microsoft themselves have said that they're starting to list progressive web apps within the store. It's a way to add more apps into a store that just doesn't have many apps. It wouldn't surprise me if they kill off their native altogether and start really embracing this combination. I also think an interesting one, a new DOM alternative will emerge. I've been talking about the weaknesses of JavaScript as a language, how it was invented in a couple of days, and a couple of weeks, give him a chance. It was invented in a couple of weeks, and as a result, it was never designed for what we're doing with it today. I have the same feeling about the DOM every time I really look at it and think hard. That the DOM was fundamentally designed for rendering static text documents like Wikipedia. These days, companies like the one I work for, we write complicated apps. The DOM was never designed to do that. One day, I think an alternative will emerge which is more aligned with what we do with it. Has anyone heard of Houdini? Houdini CSS? Yeah, okay. So again, I only heard about that recently, and it does feel like there's a glimmer of light. So for people that have not heard of Houdini, it's a set of APIs that allow you to intercept the various stages of DOM layout and rendering. So some of the things where there are things like CSS Grid. If you want to polyfill CSS Grid, it's actually quite hard to do it without causing a real thrashing and lots of render cycles in the browser. Houdini CSS allows you to intercept things like the layout steps and the render steps, so you can actually extend CSS and layout in a much more meaningful way. So maybe that's on its way already. It's just no one seems to have heard about it. Finally, or almost finally, I think JavaScript's monopoly will be lost and its popularity will fade. That's not because I don't like it. I quite like JavaScript, but I think it's inevitable. It's had this ubiquity, it's had this privileged position for 20 years, and it's going to start losing that. So I do think its popularity will fade as popular languages like Rust and C# start to get a bit of market share in the browser. But at the same time, I think there'll be more around for all of us. I think the ubiquity of the web will extend even further as it starts to move into things like Ethereum and blockchain. WebAssembly within Node makes Node a much more powerful runtime. WebAssembly on progressive web apps on mobile makes it a much more powerful runtime. So whilst the JavaScript's popularity might fade, I think the web will get bigger. So we'll still have a share of it. And that's WebAssembly and the death or future of JavaScript. You can decide which one for all for yourself. And yeah, I've got loads of links to some of the things that I showed you there. But yeah, thanks for listening. And if you've got any questions, throw them at me now. Oh, you've been itching there, haven't you?
How much do you think IE11 will hold back, like the deployment of WebAssembly?
Yeah, I don't know what it's like for you guys. Within the financial domain, IE has become, well, historically was a huge problem. There are lots of banks that until quite recently still had things like IE6 as their browser, and then it moved to IE8, which was still equally offensive, and then you get to 9, 10, 11, and the level of offensiveness decreases. But many of our clients, and these are big investment banks, have actually started moving to Edge and actually allowing people to run Chrome, which is quite surprising within a banking environment. So I think the rate at which the people upgrade their browsers, the evergreen browsers as well, does hopefully mean that the long tail of browser support isn't such an impact anymore. So I don't think it will hold things back that much. Also, a few of the techniques I've talked about are written using the LLVM compiler or the mscriptum compiler. That also gives you the opportunity to compile your Rust code or your C code to ASM.js, which will work anywhere. So it does mean that you don't need a polyfill. You can actually polyfill WebAssembly. I've been working on an open source project called WebAssembly.js. You can probably guess what it is. It's a JavaScript runtime for WebAssembly. Now, when we wrote this, we thought it would be a fun polyfill. We created it. Boy, was it slow. It was mega slow. So that part, probably not much use. But the part that has become useful, and at the time when we were doing it, we didn't realize, was we've obviously written the parser that will parse the WebAssembly binary format into a WebAssembly abstract syntax tree. that has a lot of value for Webpack. So Webpack uses our AST and WASM parser. So for example, Webpack can tree shake. So do you know tree shaking? Yeah, so it can tree shake all the way from JavaScript to WebAssembly. So it can shake out the parts of your WebAssembly module that aren't being used. That was a long answer. What was the question again? Browsers. I'm with every year, I'm more optimistic that the long tail of browsers is not such an issue as it used to be, in simple terms.
There must be. There are some offices, big offices in Sweden, that has a lot of IE11 because we have a lot of visitors coming in.
Yeah, so you're not the only ones. We always thought that we were unfortunate having to deal with IE 6, 7, 8. These days, we do still have applications we're developing that have to work on IE 9, I think. Most have gone for IE 11, and a few of the applications we're writing are Edge and the other good ones.
I have more questions, but I leave some room for... Go ahead. Do you know how involved are you in React? Do you know how it works?
Involved, and I use React quite a lot. Yeah, it's a good toolkit.
Do you see any good application of WebAssembly to speed up the React?
Yeah. There's a talk that Lynn Clark did. Have you heard of Lynn Clark? If you've seen any of the code cartoons that she does on the Mozilla blog, she's really great developer, but one of the best things about Lynn is she's brilliant at explaining things. Actually, there's a link to it here. A cartoon intro to WebAssembly is a great introduction. She did a talk on WebAssembly within React. There are a few. At the moment, WebAssembly is ideal for more algorithmic tasks. So things like DOM diffing is a good example. I haven't seen an implementation of React that uses WebAssembly, but Ember.js are using it. So Ember.js have a thing called the Glimmer VM, which is their rendering engine. And it is actually a VM. So the way that one of the things they did was most UI frameworks have some kind of templating format where you mix HTML and you mix some code together. What they decided to do was actually compile that template at compilation time into a small instruction set. So basically instructing their VM, okay, grab this DOM element, change this property. And they created their own binary format that ships to the browser and runs in their own VM, which is a pretty cool idea. What they've done is they've replaced their current VM with a WebAssembly VM to make their VM run faster. So the Glimmer VM, which sits inside Ember, has been rewritten in WebAssembly using Rust. So again, at the moment, it's finding those sweet spots, because before host bindings come along, you wouldn't easily be able to take a whole framework and just change the lot of it. It's got to be something fairly algorithmic. It's got to be something that isn't going to do too much back and forth across the JavaScript WebAssembly boundary because of the performance implications there. So again, React, things like the DOM diffing part of React. But to be honest, most React programs run slow because you're using it wrong. It's a classic. Angular was the worst for that. AngularJS before Angular 2 with all the watches and things like that. So, yeah.
So would you say that a very good use case today is you have some huge calculation you want to do, and you prepare the WebAssembly, and then you get one answer back, but actually going back and forth is...
Well, actually, on the Mozilla blog, they have significantly improved the speed of that boundary. We're talking orders of magnitude changes. So again, a lot of this stuff, the performance characteristics you see now are not the final performance characteristics. It would be a bit like comparing the performance of JavaScript 10 years ago to the performance now. We are going to see the performance of WebAssembly increase significantly before it starts to plateau. But at the moment, algorithmic kinds of tasks are more appropriate. Things like hashing algorithms, crypto algorithms, things like the stuff I showed you, binary decoders. I'm quite surprised things like AutoCAD though, because I think for AutoCAD it's doing a lot of graphics. They were probably very careful about the cut they made, where they compiled to WebAssembly and where they would obviously have to put a JavaScript layer on that writes to canvas rather than the native graphics they were using. So yeah, you've got to be careful about what you use it for at the moment. Any other questions? All right, thanks for listening.
Thank you so much.
Cheers.
Maybe we have questions from the stream somehow?
I didn't see anything of that, but I did see other people watching the stream.
Cool.
Yeah, we have. Yeah.
Do you guys use Rust or any other languages, or are you pretty much JavaScript?
Yeah, I've tried it out, but not for anything we have in production.
Yeah,
yet.
yeah, we don't use it in production. It is a nice looking language.
It's a really nice language.
So what do you use on the server side?